for sticking to the very end. So I would like to take you on a short trip down the rabbit hole I fell into during some other analysis, and this was like the pet project, and out of the sudden became one of the things which I'm really excited and passionate about. So over the course of last 2 days, as well as in our everyday work, we are discussing those exciting models, opportunities, what we can map, but very rarely, especially recently, we are discussing how variable in time and space are our data. And this is something which maybe is because right now we have all those cloud capabilities, and basically with a single line of the code we have access to the whole archive. And somehow we are forgetting that those data are limited in time and space. And today I would like to show you why it might be important, or why it is important for what we are doing. And it's not only important for time series analysis, which are very dear to my heart because I'm doing time series analysis. So this is a Landsat dashboard view when for each tile we have a summary how many acquisitions was made for a specific time. This is also important for Sentinel, and those two sensors are going to be an example for my talk. And again, we have this summary of products again for each tile. But this is nice information to have, but this is not really information we need to parameterize our models, because along those acquisitions and the history of different hotspots being sensed more frequently for different reasons, we have cloud cover and snow cover. And those two decrease actual availability of usable data quite significantly. And somehow we need to parameterize our model, we need to have those usable data, which means that we should run data availability for each of our studies beforehand, and we are not doing it. So also, like, for many models, we are not obviously using raw data like those single day acquisitions, because those are messy data, a lot of holes, a lot of also, like, those are heavy data in terms of terabytes. So what's also very common in machine learning is that we are compositing them, or data binning, or data bucketing, if you will, which means we are taking our time series of single day data, and we are composing a time series of M composite each year, each representing n days. We can use different algorithms to do it. I'm not going to go into details because there are different differences, and for different purposes, different algorithms might work better. On top of it, we can also apply data interpolation. And this solves two prerequisites for machine learning, which is that many machine learning models require data which are acquired at the same, or represent time points equally distributed in time, and also quite a lot of algorithms are dealing very poorly with data gaps. And as we saw yesterday, with I think it was Greg who showed this, with a single click we can have 10-day composite for our time series of choice. And right away at that point in my head went red or yellow light. Okay, we can, but not for all the points or like locations in time. Because with machine learning algorithms, or any algorithm, we can create this synthetic 10-day composite time series, but we can sometimes do it on 3 points. And the question is like, okay, how good, how accurate is our time series? Because the algorithms can produce whatever we want. we can then take this 10-day composite time series for granted, do a research, publish it, some decisions will be made on it, and then we are facing this another thing we discussed yesterday, so ethics. So we believed our results were super great, but fitting a time series of 10-day composites on, let's say, 5 points for a year will work, and for some applications might be enough, but for many it's not. And so basically what we miss in our discussions is like, what is the best or feasible compositing window for our specific area, time window, and application. And as a community, I'm sorry to say, we are doing here heuristic fallacy, because we are typically eyeballing, believing that we are an expert and we know what's really the data, the distribution of usable data. And we are not alone in our fallacy. Other domains have similar problems, but I hope that you will what you will get from my talk is that we should be very careful. And please demonstrate me I would like to demonstrate to you why we should do so. So let's say we want to do forest monitoring for disturbances. Let's go crazy, 8421, some studies are doing it. Let's maximize our chances of success, Landsat plus Sentinel, great. From the land render legacy, we know that enough to do it is a single observation per year. Sometimes it's a maximum value composite for a growing season, for a complete year. Doesn't matter, single observation per year, data as they are in the archive, excluding clouds, shades, and snow. And for Europe, we can see right away that, yes, there are some forested areas which are meeting our requirements of 38 data points for the complete time series, but there's also quite a lot of forests for which we'll have much fewer data points, which means if we are having an algorithm running on it, the accuracy and certainty of our results for those more bluish and greenish pixels are going to be lower. And of course, you can see on those two side panels the summary for latitude and longitude against time, that the problem is quite often in the early years of the Landsat archive, fair enough for Europe, but also there are some data gaps in 2000s and 90s and 2010s. Another example, vegetation monitoring, land cover change, for example, land amendment or simple phenology to identify different crops. Again, let's go crazy. Landsat and Sentinel, monthly composites. This is like a standard, go-to standard in many of our research. But let's limit ourselves to growing season because we are looking for phenology. Snow is not really of our interest here. It's not looking good. At least as how I would like to see it. And those are raw data, right? Still, very few pixels are really showing that for more than 20 years in our complete time series, we have enough data for a growing season, only growing season, which means that for the remaining 18 years or more, our algorithm could or might produce a result, but these results might not be to the standard we hope for. But you heard me say, okay, we have data interpolation, so let's imagine a scenario that very generously we can interpolate up to 50% of composites each year, which means, okay, if we are using monthly composites, it means that for the complete year, calendar year, we need minimum 6 months with the data, composites, so cloud-free or almost cloud-free, and with our fantastic data interpolation algorithm, we are able to confidently and accurately fill in the data for the remaining 6 months, right? So how our data coverage looks like for the same example, only data interpolation, much better. But yet again, for Europe, we are not getting a complete time series, which means, for example, if we are training our algorithm or developing our algorithm in a specific area like Ukraine, where we have relatively good data coverage for the complete time series, and we want to translate the same algorithm to area like France or, God forbid, Ireland. It's going to be a very difficult task. In a sense, we might, depending what algorithm and how we script it, our algorithm might produce the results, but the quality of this result will be completely different what we expect or what we want. And this comes into play not only already at the quite local level, and of course, pan-European or global analysis are not always on the scope for all of us, but those differences start to come into play already at relatively low local resolution, right? We can also turn the question around and ask, what's the shortest compositing window? Again, assuming this generous 50% data interpolation case, which is sufficient for each year to give us this complete time series at the very end. And you see right away that the most recent years are showing in blues, which means that 5 and 10 days composites are completely fine. If we are fine with this crazy interpolation of 50% and our algorithm is fine, is working well. But for the early years or 90s or 2000s even, this is becoming really problematic because we don't have complete and consistent data coverage. Just steals from this animation, and you see the spatial and temporal variability. This is for calendar year, okay, so again, an exercise, let's look how it looks for growing season only. The situation looks slightly better, more oranges and greens, but if you were paying attention to the Mediterranean regions, here, if we are limiting ourselves to a growing season, you may notice that for some regions we are getting now longer compositing periods in a sense that we overall have fewer observations because growing season in Mediterranean, which is a dry region, happens during the wet season. So we have more clouds and higher precipitation, more clouds, so the chances for clear sky observations are lower. But for sure, you also notice those lovely stripes in all of my figures, and those are not errors, those are not artifacts, those are really how the data look like due to orbit overlaps. And this is something which we in some regions can benefit from, because here we have twice or thrice as many observations than here. But this is also, again, something which we should bulletproof our models against and be mindful to have the results with the same accuracy all across the board. And you can see, like, even if we would like to do analysis for Brandenburg, so the area around Berlin, will face this issue. And this is a real issue. Just to quickly put it into like the big picture perspective. So whenever we are doing analysis with different models, and again, some models might be more robust against this problem than the others, we were facing those three limitations. So those which are coming from sensor, those which are coming from environment, and we cannot really negotiate with them. And those which are really coming from the specification of our analysis. And ideally, we would like all those limitations to come together nicely to allow us to have nice results with the same credibility all across the board. However, it's very often not the case, and we need to compromise, and we need to find the solutions, and maybe we need to use different algorithms and models to really make sure that our results are to the standards we want them to be. So quickly wrap it up. All the All the figures you've seen are coming from our study on usable observation over Europe. We use for it Landsat and Sentinel time series, and we masked out all the cloud, shadow, and snow-related pixels. It was done in Google Earth Engine. But this is like the sample data set, so wall-to-wall, but sampled in a regular grid of roughly 20 kilometers, and growing season information comes from MODI's vegetation dynamic product. Since then, we extended it to the complete world because Europe is only a small sliver of the land, and the craziness of heterogeneity of temporal and spatial patterns of data availability of usable data over world are really striking. And if someone would like to do a time series analysis for the complete world, this is something we need to consider and include in our models. If you would like to check those data for yourself right now, it's available as in a Google Earth Engine app. Once the publications are out, it will be freely available, so you could really check it. Something is popping up here, sorry. Check it really for your test study and time of your analysis to understand how it works. Yeah, if you really would like to dive into the details of all the methodology, I would point you to those two right now preprints, hopefully soon fully fledged papers, as both are under revision in peer-reviewed journals. And yeah, with that, I'm happy to take your questions if you would like to connect. There are details on the slide. And yeah, thank you.
Yeah, thank you so much for the great talk, pointing out those limitations in satellite data and time series. Is there any questions from the audience to the speaker? Yeah.
Thanks. Sorry for all the questions. I was wondering, yeah, you mentioned you're going to publish this data as on Google Earth Engine, or as a Google Earth Engine app. I was wondering, did you produce this on Google Earth Engine? And I was also thinking, have you considered reaching out to the Copernicus data space ecosystem? Because this looks like a really valuable asset for anyone looking at what is the coverage for my region of interest, and are there spatial differences and all these things?
So yeah, if it didn't come clearly, yes, we did all the analysis on Google Earth Engine. We are, the data are to be browsed through Google Earth Engine app. The data will be available through the RIAD as CSV. So there are some limitations in the Google Earth Engine app. So right now you can query only a single year. So if someone would like to check how the situation looks like from 2017 to 2022, it's not right now easily achievable in the app. No, we haven't really thought about reaching out to Sentinel. The other way around. So this research taps into Landsat scientific team. So in a sense, it will be like the Landsat team is already aware of this research, but I don't think they will really want to or have capacity to feature it somewhere. So right now, we as a Humboldt University will foster the data and take care of dissemination. But if you have ideas who to contact, yeah, I'm all ears. Yes. Sorry for 10-day composite run.
I misunderstood this as a question. Was there another question, or yeah?
I mean, first a comment. This is the time. Also, this is interesting from ESA point of view because we are working on Sentinel-2 next generation. So there we are defining which will be the the orbit of the new satellite. So that makes sense to have information there. And since we are working together with Landsat, so Landsat next generation will go together with Sentinel-2 next generation. This is very important. So I, let's say, stress what has been just said to distribute this information. One question is basically that this is the question is, this was the comment. The question is about the fact that here you're talking about limitation for vegetation monitoring. That's one specific type of application. And let's say, and even that, you need, in my opinion, to clarify very well what you mean by vegetation monitoring. Is vegetation meaning crops, meaning because you were talking about harvesting season, you think about, let's say, other type of vegetation, let's say, because there are other issues related to, for instance, you need to know, from the European point of view, when you are not using a specific field. And for that, maybe the data is enough, maybe. That's another question. I mean, and again, I think that one thing which is very important, sorry, that's an additional comment, is, and I'm ending, sorry, it's basically the fact that sometimes definitions are very important. There was someone on GC today saying that definition of things is very important, and I guess here as well. Thank you.
Okay, if I manage to recall all your points, so yeah, vegetation in this case means everything which is getting green at any point in time. Probably this data set might be a little bit less appropriate for example, urban monitoring is due to cloud masking in Sentinel-2. So we are not using in this scenario Sen2Core specific mask because we know that sometimes there is this mismatch between high-rise or even low-rise urban areas and specific types of clouds. So how we deal with cloud masking for Sentinel in Google Earth Engine is a little bit of the Frankenstein. So we are getting like the cloud probability, we are getting cloud displacement, we are also using thresholds on the Sirius band from 1C level. We are at top of it also projecting clouds and shadows, which is probably the most computationally expensive part of this. So there might be, depending, this is like tapping to a completely different huge discussion of how good is our cloud masking in general. I'm confident that this data set might be very useful for other studies outside vegetation land covers. However, I'm most confident that our cloud masking is the best for our vegetation-related areas. It's, however, like the point of the talk, beside pitching the data set, which I'm personally very proud of, is to draw attention of the community that we have those huge temporal and spatial variability, and it also is not limited to Landsat. It's also, if we want to perform analysis with Sentinel-2 for a single year, we will come those are limitations we need to deal with. And the third part of the question, sorry. I'm happy to chat afterwards.